Okay, so good morning. Let's get going with the discussion on gate sizing, right? So we were discussing gate sizing, right? So the problem here is the inverse of what we solved earlier. Earlier you were given certain sizes of gates and you were asked to calculate the delay. Now we are solving the inverse problem. We want to minimize the delay between the source and the destination, and in the process find the size of the gates in the path. Okay, so basically it's like this. You have, let's say, an inverter, maybe some NAND 2, NAND 2, then NOR 2, maybe NAND 3, it doesn't matter, or NAND 4, all the way to final inverter, and then you have a load capacitance CL. Okay, let's assume that without loss of generality that this first inverter is a unit sized inverter, right? So this is just a 1x inverter, and let's say that this is some 100x of the unit inverter's capacitance. So we will normalize everything like this to the unit inverter's capacitance. Okay, so let's say that this had a capacitance of 3C. Then I am saying this is nothing but a capacitance of 300C. Okay, normalized capacitance. So now what we want to find is what should be the gate sizes, right? So this has to be scaled up by a factor of K1, this by a factor of K2, K3 and so on, right? And then Kn. So there are n plus 1 gates in this path, okay, and I want to find out the thing, or let me just make it n gates, makes it easier. Okay, so this is what I have. N is the number of gates in the path. Now earlier, if you remember, we were dealing with the gate size or the gate scaling, 1x, 2x, 3x as the variable, right? The problem is if you use that as the variable, then you need to explicitly calculate the capacitance at each gate depending on the type of the gate. For example, if it's a NAND 2, then a unit gate has a capacitance of 4C. If I scale it up by a factor of K1, then it has to become 4K1C. Now for NOR 2, it will become 5K1C and so on. I need to actually make a lot of complicated calculations to just obtain the capacitance correctly. So therefore the variables that we are going to choose here are xk's, which is nothing but the capacitance, input capacitance of the k plus 1th gate. Okay, so this I am saying is x1. x0 is this 3C, whatever that capacitance is. Okay, and this will be my x2, right? x2 is the input capacitance of the k plus 1th gate. Okay, so like this I go and I have an input capacitance here of xn minus 1, and this is going to be my xn. Okay, so now we can calculate the delay of each stage using our logical effort formula that we had derived earlier. So we said that the delay of the kth stage, dk, normalized delay, is gk into hk plus pk. Gk is the logical effort of the kth stage, hk is the electrical effort of the kth stage. Electrical effort is output capacitance by input capacitance. just this ratio. Clear? So what do I now want to do? I want to minimize I want to minimize the delay d, which is nothing but the summation of dk and k going from 1 to n. Okay. I want to minimize this, and my variables are x1, x2, xn, right? Actually xn and x0 are fixed. I have to find the other n minus 1 variables in between. Okay. So now let's go ahead and solve this problem. D is equal to summation of gk into hk plus pk. So this I will write as summation of gk into hk plus summation pk. Now we already discussed that the parasitic effort or the parasitic delay is independent of gate size to a first order. Whether you scale it up by 2x or 4x, it doesn't matter. The parasitic delay is not a function of my input capacitance variables that I am talking about. So this is not a function of x0, x1, xn. Therefore, it's a constant and it is not going to alter my minimization problem. It's a positive constant. I can just remove that from my minimization problem. And this is the reason I also told you it doesn't matter whether you calculate the parasitic delay as using the Elmore delay for the worst case, right? Whether it's 6 RC or 7 RC, it doesn't matter because it's a constant that doesn't affect your gate sizing problem. You can be more accurate, calculate with full Elmore delay or not, it doesn't matter. Okay, that's why that approximation is okay. It's not a big problem there. So now I want to minimize summation gk into hk. Okay, let fk equals this product hk. So what is hk? Is the electrical effort of the kth gate, which is output load capacitance, right? Output load cap divided by input cap. Okay. So here I am assuming, by the way, in this whole notation I am assuming that there is no branching. So I don't have gates like this. Okay, otherwise this notation will not work. Okay, so let's just keep that in mind. Yeah. Okay. So what is hk? It is simply going to be x k divided by x k minus 1. xk is basically what? The output input cap of the k plus 1th gate. That's what I have said, which is nothing but the load of the kth gate, right? Therefore, this is just xk by xk minus 1. And now what about gk? gk is now again a constant which is independent of gate size. That's the whole idea of writing delay like this. gk is the logical effort. Again, it is independent of x0, x1, xn, right? So it's a constant that I'm going to multiply it with. Okay. So let's now look at this number. Okay. I'm going to look at the product k equals 1 to n of fk. This is nothing but product of gk into hk. right? So I am going to now write this as a product of G into H, okay, where G is nothing but the product of G case, K equals 1 to N, and H is nothing but product of H case. Right? So what does this look like now? Product of G case, G, is nothing but a constant, some constant number. You are multiplying many logical efforts. Depending on what gates you put in the path, you will get a constant number. Okay, and this capital G is called the path logical effort. Okay, what about this capital H, which is product of H case? It's nothing but x1 by x0 into x2 by x1 all the way to xn by xn minus 1. So this is the other advantage of choosing our variables as the capacitance. Everything will cancel for H and you will simply get the path electrical effort, capital H, as ratio of output capacitance by input capacitance. Ratio of the final capacitance, which is again a constant number. We know what the load is. We have a circuit, it's driving a load. We know that number. We know the first gate is without loss of generality. I said assume that's a unit gate, right? Or that size is also known, therefore the capacitance is known. X0 is known. Therefore this capital H, which is path electrical effort, is also a constant which is independent of all the other variables, right? Again, not a function of x1, x2, xn minus 1, which are the variables of my optimization problem that I am trying to solve here. Okay. So now what do I have? I want to minimize summation Fk, right? But product of Fk's is a constant. Irrespective of what my variables are, x1 to xn minus 1, the product of Fk's is a constant. Okay, and therefore I am going to exploit this inequality of arithmetic mean is greater than or equal to geometric mean. Okay, so I am basically saying that implies summation Fk, right? Of course all these Fk's are positive numbers, right? Fk by n, which is the arithmetic mean of these n numbers, is greater than or equal to product of Fk. One to n. Yeah? Yeah. Whole power 1 by n. This is the geometric mean. And they are going to be minimum when each of these Fk's, equality will hold when each of these Fk's are equal to each other. Right? Therefore, the solution to the minimization problem is Fk is equal to G into H whole power 1 by n. Okay, and this implies that summation Fk therefore is simply going to be n times G into H whole power 1 by n. Right, which implies the minimum delay, which is basically summation of Fk plus the parasitic effort, right? Minimum delay is the summation of Fk plus summation of Pk, right, is simply going to be n into G into H whole power 1 by n plus P. Yeah. So that's where we are using the fact that this is an AMGM inequality, right? And they will be the inequality always holds. It is always greater than or equal to the GM. And we are saying that the minimum occurs when all the terms are equal. So okay, so I have tried this before. You can go ahead and do the partial derivative, equate it to 0, and you see you will get the same answer. Okay, you can try this offline and we can discuss it in the next class. I have tried it before. It will work. Okay. So what is this? Now let us say I am going to call this, let G into H equals capital F is equal to path effort. Okay, I am going to define this as the path effort. Okay, and each Fk I am going to call as stage effort. So what is this solution telling us? It is telling us that in order to minimize the delay, each gate must be doing equal amount of work. Right? For example, if I have a gate like this, okay, one more inverter and then a load capacitance. In order to minimize area, power, everything, the best thing is to keep all gates at the minimum size. Don't upsize anything. Then you would get minimum area and therefore minimum power, everything. Right? So ideally, I would like to keep this as a unit gate, this as a unit gate, this as a unit gate, this also as a unit gate. Okay, let's assume that this is a 100x capacitance in whatever scaled units. Okay, and this is a 1x gate. Now, just analyze what happens to the delay intuitively. This inverter is now seeing a 1x NAND gate. So, in some sense, if you have to put a NAND gate there, then this is the minimum load capacitance that inverter can see. And this, the fact that you have to put a NAND gate there comes from the logic function you are trying to implement. So, you have no choice. So, you have to put a NAND there. If I put a 1x gate, that's the minimum load capacitance that the inverter will see, which implies that the delay of inverter I1, I2, I3 and I4, I'm going to label the gates. Delay of I1 is therefore minimum if I keep all my gates as unit gates. Similarly, come to I2. If I have a NOR gate which is a 1x gate, then the delay will be minimum for I2. Similarly for I3. By keeping all the gates unit sized, actually most of the delays in the path are reasonably optimum. The only problem is if I do this, then the last gate I4 has to do all the work to charge that load capacitance eventually. That single inverter I4 is now driving a huge capacitance, 100x capacitance, and because it is unit sized, the resistance is extremely high and therefore the delay is very large. So what do you want to do? You want to reduce the effort that the last stage is putting in order to charge that load capacitance. How will you reduce that effort? You have to upsize this gate by some factor. If I upsize the gate, the resistance will fall by that factor and hence the delay will also fall by that factor. Load capacitance is fixed. Forget about the parasitic effort. That's a constant. I'm going to upsize this inverter by some factor and reduce the delay of the last stage. The problem is, if you increase the size of I4, you are now going to increase the load on I3. Right? The same thing will cascade all the way to I1. So the only way in order to reduce the effort on I4 is to make the other gates do more work. Now the other gates are not doing any work. They are charging unit capacitances of whatever gate it sees. Right? Idea is to split this effort across all the gates uniformly. The result is telling us that the stage effort, which is the product of the logical effort and electrical effort, should be the same for all the gates. Then your delay will be minimum.